Alright, so now moving on to Ohm's Law. So Ohm's Law is here, V equals IR, and it's a very important equation in electronics. So it relates the voltage to the current and the resistance R. And I like this little cartoon here. So you can imagine that if there's a pipe or something like that, or a tunnel maybe, we have our voltage trying to push current through, and then depending on how much resistance here in ohms, so this is our resistance. Depending on how much resistance there is, will depend to determine how quickly the amp flows through, like that. And this here, this little triangle, so this triangle here, oops, there. If you cover up, let's say you wanted to find voltage, if you cover up V, then they'll give you the equation for IR. So if you don't want to, it's just an easier way to rearrange equations. Obviously, V equals IR is not that hard to rearrange, but if you cover up R because you're looking for resistance, then you have V over I, so V over I. And if you cover up V, you have V equals I times R. And if you cover up I, then you have V over R. Okay, so some people find that useful. Now, we haven't really spoken too much about resistance formally, so we'll just quickly read about what resistance is. So if current passes easily through an object, the object has low resistance. If the current does not pass easily, the object has high resistance. The resistance depends on what the object is made of and its shape and size. It is convenient to think of resistance as in opposition to current flow. So if something has low resistance, we'll just go back up to this. Oh, didn't do that. If the current passes easily through an object, the object has low resistance, we call them a conductor. And metal, like a copper, is obviously one of our standard kind of examples of a conductor. If the current does not pass easily, the object has high resistance, and we call that an insulator. And something like, so if I put copper here, something like rubber is our classic example of an insulator. Okay, and just like I said before, the resistance is in opposition to current flow. Resistance is measured in ohms. So the ohm symbol is the Greek letter omega. Okay, letter omega, and sometimes R is used instead of the omega symbol just because they want to make it clear that it's resistance. Okay, so current is proportional to voltage. So if we look at our equation up here, if you double, so it could, because V equals IR, if you double V, then you're going to double, or if you double I, then you're going to double V and vice versa. Current is proportional to voltage, and current, so let's say, is inversely proportional to resistance. So if we rearrange it, so we have I as a subject. So inversely proportional to resistance, if you double the resistance here, then you're going to halve the current. That's what that means there. Okay. So I'll move on to some examples here. So if we have a 0.60 amp current flows through an electrical component which has a 12 volt potential difference across it, what is the resistance of the component? So let's imagine let's draw this out. So if we've got how many? 12 volts. So we've got a 12 volt battery, and we've got a resistance here, or a resistor here. That's our component. And we can just call that R. Why not? Oops. Gee, if we can. Why not? If we can draw it, that makes help. Let's write down our R. Oh, nice. Okay, so we've got 12 volts there, and we've got I going around there, and that's 0.6 amps. So one of the key things I just wanted to talk about before I do the calculation is if we've got 12 volts from this point and that point, so we've got a potential difference of 12 volts across there. It means that across this resistor, we've also got a difference of 12 volts. Okay, so whatever the difference is in the battery, there also has to be that amount of difference across the whole circuit when you have it set up like this. Anyway, so we're looking for, so our Ohm's law is V equals IR. So we want to rearrange for R, because that's what we're looking for. V over I. So we've got 12 volts divided by 0.60 amps, and that gives us a total of 20 ohms. So we've got a 20 ohm resistor, or a component with 20 ohms resistance in there. Alright, so a 100 ohm resistor has a potential difference of 12 volts across it. What current will flow through the resistor? So again, if we throw our circuit in there, why not? So we've got 12 volts in the battery, and we've got 100 ohms, or 100 R there, and then what current? So I there, and remember that I is the same everywhere. So we have this time V equals IR again, IR, so then I equals V on R, so 12 volts over 100 ohms, and that's going to be 0.12 amps. Okay, that's what I is equal to. So 15 milliamps flows through 100k resistor. Find the potential difference across the resistor. So we're not sure what our voltage is this time. Okay, so we've got 10k, and we've got 15 milliamps, and we're looking for V. Okay, so V equals IR. So remembering our prefixes, we got 15 times 10 to negative 3, and we've got 10 times 10 to the 3 for K. So that means that 10 to the negative 3 and that 10 to the 3 are actually going to cancel out, so we're left with 150 volts. 150 volts across that cell or generator or battery, whatever can produce 150 volts. Alright, in question 4, we now have a voltage that can be varied from 1 to 100 volts, so we can set it. We might have a power supply or a power pack where we could change the volts like that, and is applied to a 5 ohm resistor. Excuse me. What will be the range of currents that will flow in it? Okay, so the range, so we first need to look at range of current that will flow in it. So we've got V equals IR, like always. I equals V over R. Okay, so for 1 volt, so if we set down the bottom, 1 volt, I equals 1 volt over 5 ohms, which is equal to 0.2 amps. Alright, so for 100 volts, that's our maximum, I equals 100 over 5, which is equal to 20 amps. So, therefore, the range is 0.2 amps to 20 amps. So that's part A. Part B. How much energy will be dissipated in the resistor each second? Alright, so remembering how we had our equation volts equals energy over charge, let's remember that 1 amp is equal to 1 coulomb per second. Okay. So when V is equal to 1 volt, so for our first one, when V is equal to 1 volt and I is equal to 0.2 amps, then we can work out that the charge Q every second is going to be equal to 0.2 coulombs. Well, this coulombs per second. So per second. Okay, so the charge is 0.2 coulombs per second. And then we can put, so, and if we rearrange V equals EQ, therefore E equals V times Q. We're not responding again. I tend to have this problem quite a bit with this computer. Hopefully it'll take too long. Good. Oops. Okay, so E is equal to, okay, good. Come on, computer. So E is equal to V times Q, which is equal to 1 volt times by 0.2 coulombs, which is equal to 0.2 joules. Okay, so when V is equal to, how much space do I have there? V is equal to 100 volts and I equals 20 amps, then Q is equal to 20 coulombs per second. Therefore, energy every second is equal to 100 volts times by 20 coulombs per second, or 20 coulombs. That's equal to 2,000 joules, or 2 kilojoules of energy. All right.